Congratulations, you have made it to the final session of Sampling for Forensic Practitioners, a CSAFE short course sponsored by NIST. Quite frankly, I'm proud of you. This is tough. I think if you've stuck with us this whole time, you probably deserve an award of some sort. I tell you what, at the end of this session, I will send you a certificate. We have the luxury of having two speakers today. Dr. Alicia Carriquiry joins us for the third session, still as the Distinguished Professor and President's Chair in the Department of Statistics at Iowa State University and the co-founder and director of the Center for Statistics and Applications in Forensic Evidence. The new addition today is Graduate Research Assistant Joe Zemmels. He's been with CSAFE for quite a while now, and I'm not sure his Graduate Research Assistant title accurately describes the level of contribution that he brings to the work we do, but you will see that he is a fantastic addition and will provide a lot of value today in the practicum. Alicia, I'll let you start off.
So as promised, today I'm going to give a brief intro to the Bayesian approach to estimation and sampling. And I don't want to spend a whole lot of time on this because I really want to give Joe as much time as possible to show you how to implement some of these things. He's not going to get into the Bayesian approach, but I've been thinking about whether we should try to implement some of the things for you, maybe create some sort of easy to use software, because I've been looking around and there's really not very much out there that is useful for practitioners. So everything we've been talking about until now has been based on the frequentist approach to statistics, and that's what you see most often. But in the forensics world, there's a lot of talk about Bayes factors and Bayesian estimation, and in my experience, oftentimes people don't really understand the differences between the frequentist approach and the Bayesian approach. So that's what I'm going to try and talk a little bit about today, with an emphasis on sampling. And I am just going to stay in the simplest possible case where we have a large population, and what we want to estimate is the population proportion of items that exhibit some sort of trait. So the population of pen drives, that the proportion of the pen drives in the shipment that contain pornography, or the proportion of transactions in some company that are fraudulent, or the proportion of tablets in some sort of seizure that are that contain drugs. So that's what I'm going to refer to, the very simplest case. But before I go there, I will start with a very brief primer on the differences between the frequentist approach and to the world and the Bayesian approach to the world. So in the frequentist world, which is the world we inhabit most often when we talk about statistics, parameters, for example, the population attributes, those are fixed in the sense that there is some true proportion of something in the population. I don't know what it is, but I would like to estimate it. And everything that we do in the frequentist world relies on this idea of repeated sampling. So there's this population, and the idea here is that I could take any number of different samples of size n, let's say, from that population, and these samples are random, and we discuss this idea of a sampling distribution of the sample estimate, which allows us to describe the variability of the sample estimate across all possible samples we could obtain from a population. So we talked about the fact that, let's suppose that I have a sample of size n, and I want to estimate pi. And what I do is I compute P, which is the number of positive cases in the sample divided by the sample size. And I said, this is great, except that if I were to draw a different sample of the same size, I would get a different P. And I would get a different P every time I look at a different sample. And so what's the story? And so we said, yes, in order to understand whether my P, the one that I get from the one sample I actually take, is any good, I think about these two ideas. One of them is the idea of unbiasedness, and the other one is this idea of sampling error. And the unbiasedness just tells us that if I have a random sample, on the average, the statistic is going to be equal to the population parameter. So what does that mean? It means if I were to take 100 samples of size n, on each one compute P, and then average all those P's, that average is going to be pretty close to pi if in fact my samples are random. That's one idea. The other idea is this idea of sampling error, which is how close can I expect my P to be to the true pi? I don't know that, but if I know what the sampling error for P is, then that gives me some idea of what I can expect in terms of the difference between my P and pi. And both of these ideas are based on this abstract notion of repeated sampling from the same population. And randomness here arises through this sampling process. So pi is fixed. What's random are the data, because that's what, I use this random approach to draw the sample from the population. So the observations are random that I am working with, and therefore anything that I compute using those observations is also random. So the random quantity here would be the sample statistic. And that's why I think in terms of a distribution, a sampling distribution for the sample statistic. All right. So in the Bayesian world, things are exactly the other way around. So in the Bayesian world, the idea is that I only have one sample. And so this notion of repeated sampling, this abstract concept of repeated sampling, and on relying on data I have never observed, this is not a Bayesian idea. So in the Bayesian world, we say that once we have observed those data, once I have drawn my sample and observed the data are fixed. Those are the data on which I am going to rely in order to say something about the population quantity of interest. Now, Bayesians act as if parameters were random. It's not that Bayesians believe that parameters are random. Bayesians also understand that parameters are some fixed quantity that is unknown to us. But Bayesians use the machinery of probability, all the tools that probability provides, to reflect the uncertainty that we have about the true value of the parameter. So it's not that parameters are random, but we treat them as random only because we don't know what the true value are. And so in the Bayesian world, instead of coming up with an estimate P for example, the population proportion, what we're going to be computing is a distribution of likely values for pi. So P is my best guess for pi if I am a frequentist. If I am a Bayesian, I will give you a whole lot of values that I think are likely values for the true unknown pi. So the frequentists and the Bayesian people have a completely inverted view of the world. The frequentist says, if I know something about the population proportion, then I can tell you what to expect if I draw a sample from that population. the Bayesian says, I have a sample. Given that sample, what can I say about the population parameter? Oh, and here I used a different notation. Theta here represents any parameter. It could be pi, it could be mu, the mean, it could be sigma, the standard deviation, it could be anything. I just use this generic symbol to denote a parameter. So the frequentists, in a sense, we are all Bayesians. You know, frequentist statistics is much more prevalent, but we are all Bayesians because this is the way we humans think, right? I have a sample. What does the sample tell me about the population from which it came? The frequentist has this funny way of thinking about it, which is, I have a population, and if I were to know theta, what would that tell me about the data? You know, and if I were to draw, if I know theta and I were to draw a sample from that population, what can I say about this, what I am going to be observing in the sample? All right. So the funny thing is that in some simple cases, the actual results are going to be the same if you're a frequentist or a Bayesian. So you end up with the same numerical results. The interpretation of what you get is completely different. And we'll do an example in a minute. All right, so Bayesians rely on this theorem called Bayes' rule or Bayes' theorem. And Bayes here is the name of the person that proposed this approach back in 1763. Thomas Bayes was he was a mathematician and a philosopher and a pastor in the Church of England, and he was the one that proposed combining information in order to say something about a population quantity. And so he said, suppose you have any old parameter theta, let's say a mean or a proportion or something. And you want to say something about theta, so how do you go about this? And he said, well, you know, what we should do is use all the information that's available about theta. And he said, in addition to the information that is contributed by data, there might be some prior information we have about theta. So for example, you know, if I have a shipment of little bags that contain some white powder that comes out of Thailand, just to say something, I may be pretty suspicious even before I do any analysis that those baggies contain something that's awfully, you know, similar to cocaine, what I would expect cocaine to look like. And so my prior belief might be that, you know, the shipment comes from a drug exporting country. It is packaged in the way I would expect drugs to be packaged, blah, 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 you know. So I may have all this information that may lead me to believe that the probability that there's drugs in that shipment is very high. So that's what I would call the prior information about the parameter of interest. And then I start from this prior information, and then I collect a sample. I sample baggies and analyze them, and I see what proportion of those baggies contain drugs. And so that would give me the sample data. So this is the second part here is identical with what a frequentist person would do, except that as a Bayesian, you also have this other source of information, this prior information that you want to incorporate into the analysis. Well, to reflect this prior information, Bayesians come up with something called a prior distribution that, you know, oftentimes you will see written with this formula, the probability associated with different values of this parameter. In the case of pi, the population proportion, this probability model might be something, would be something that assigns values to, assigns probability to values of theta between 0, to values of pi between 0 and 1, because it's a proportion. Then we have the data, let's say the observations y, and in order to incorporate that information into the model, I use this thing called the likelihood function. And we didn't talk about this before, but the likelihood function is what the frequentist people use too. This is the model that I use to represent the data. And when we were talking, for example, about sampling from a very large population with replacement, we said that, when you were looking at so y here was the number of positive cases in your sample, we said a good model for this would be the binomial model. And remember when we were in the weeds, well, that's what's called the likelihood function in this case. So that's the name that's used. And so if you combine both of these distributions, and this here just reads the probability of observing what I observed given the value of the parameter, the population parameter. And so if you combine these two distributions using Bayes' rule, and Bayes' rule tells you how to do this, then you obtain a third distribution called the posterior distribution. And the posterior distribution oftentimes is written in this way. It tells you what are the likely values of the parameter. So what are the likely values of theta in this case, given what I have observed in the data and given my prior information. So the frequentists rely on this distribution, on the likelihood model or the probability model for the data in order to say something about theta. The Bayesians rely on the posterior distribution to say something about theta. Okay, so those are two different ways to, those are two different probability models that people use to say something about the population parameter. All right, so this is the way, this is just a formula, but this is the way you would write Bayes' rule. So what I do is I start from a model, a distribution that tells me about what do I know about the parameter of interest before I observe any data. So that's my prior. So we read this from right to left. I combine that with the model I adopt for the data. So I obtain my sample, I made my measurements, I get my Y's. And so I decide that this is a good probability model for my data. And by combining these two densities or these two distributions, I get something called the posterior distribution, which is what we have on the left over here. And this weird symbol simply means proportional to, because there's a piece missing here so that to rescale everything to the right values that I didn't write over here. Now, sometimes it's a little tricky to come up with this. So this distribution, this likelihood function, this likelihood model, everybody has to have one of these. The frequentists, the Bayesians, everybody has to have one of these because this is what tells you what the data look like. So you may have a normal model or a Poisson model or a binomial model, some model. You have to have a, so everybody needs to come up with this one. It's sometimes hidden. So, you know, we didn't talk about a model when we started this course, but there's always in the background, there's always a model. And, but this one is something that the Bayesians, only the Bayesians have to come up with. And sometimes it's a little tricky to come up with a model to represent my knowledge about the population before I collect any data. But there's some convenient choices. And by convenient, I mean mathematically convenient choices that make this calculation simple, or simpler, I should say. And those conveniently mathematical options oftentimes work fine. And so we're going to see one such convenient option in the next couple of slides. So let's do an example to put all this stuff, to land all this stuff more or less. The simplest possible case, we have a large population. We want to estimate the population proportion of something, of some attribute. And so the observations here, so let's suppose I draw a sample of size n from that population. And here, each one of these items, sample items, either have or do not have the attribute that I'm thinking about. So each one of these x's is either a 0 or a 1, let's say. So remember we said if that's the type of data you have, a model for each one of these x's would be a Bernoulli model with a probability of success pi. And then we said, if I count the number of successes, so if I count how many of these x's, n x's is positive, then I get y, which is the number of items in the sample that exhibit the attribute of interest. And remember, we said a good model for y is this binomial model, and this binomial model depends on the sample size and on the probability of success of each individual sample item. And this is what I'm calling the likelihood function. We didn't call it this when we talked last Friday, but this is what we call the likelihood function. And I know what to do if I'm a frequentist person. If I'm a frequentist person, I'm going to take the sample data and obtain a point estimate, a best guess for pi. And my estimate for pi is just p, which is the number of positive cases divided by the sample size. And so that's very simple to compute. And remember, we talked about the margin of error and the sampling error of p. And we said the standard error of p, remember it was computed as p times 1 minus p divided by n, square root of that. And you can find that in last week's slides. And then, so, and 1.96, we used 2, I think. We said if I want a 95% confidence interval for the true population proportion, I computed by taking p plus minus the margin of error. And we said the margin of error is just 2, we use the approximation, 2 times the standard error, but I could also use the real value, which is 1.96 times the standard error. How do I interpret this confidence interval? So if I remember what we said, the confidence interval is just one of many I could have gotten if, in fact, I had drawn many samples of size n from this population. And therefore, this confidence interval is a random quantity, right? So the way I explain this to people is the following. I would say, I am 95% confident that this particular interval contains or covers the true value of pi. So you can imagine that pi is sitting somewhere, and what's moving around depending on the sample is the confidence interval. So my confidence interval either covers pi or doesn't cover pi. But what I'm trying to say here is if I had 100 intervals that I computed, then 95 of those would cover and 5 of those would not. And I, of course, don't know whether the one that I have covers or doesn't, but I'm 95% confident that it does. So that's the interpretation from a frequentist point of view. What would the Bayesian do for the exact same problem? Well, the Bayesian would rely on the same data and the same likelihood function, so the same binomial model. But the Bayesian, remember, needs to come up with a probability model that will reflect my beliefs, my prior knowledge about pi, the population proportion, even before I observe any data. Well, so let's think about what this pi is. So pi has to be positive because it's a proportion. And furthermore, it has to be between 0 and 1. So pi cannot be 73 because pi is the probability of success. And so it has to be between 0 and 1. And so if you think about the different probability models out there, you need to think about one that's appropriate for this type of variable. For example, the variable that can only take on values between 0 and 1. And it turns out that there's this model out there called the beta model, so the beta distribution. And that's a standard model that is used to reflect prior knowledge about pi when the data are 0, 1, so categorical data. The beta distribution, much like the normal distribution, the binomial distribution, has some parameters itself. So it has two parameters, A and B, and these parameters, depending on what you pick for these parameters, is the shape that this distribution is going to have. So I'll show you the next slide a few examples of that. But before we go there, it turns out that the product of a beta prior and a binomial likelihood is also a beta distribution. So this is what I mean by convenient. The beta prior is called conjugate to the binomial likelihood. What does it mean to have a conjugate prior? It means that if I take the prior and multiply it by the likelihood, the posterior is going to be in the same form as the prior. So in this case, I have a beta prior, a binomial likelihood. I know that the posterior is going to be also a prior, a beta. And the question is, what are the parameters of that beta? And it turns out it's very simple to compute. It's going to be a beta distribution with parameters A, this A, plus the number of successes. And then instead of B, it's going to be B plus the sample size minus the number of successes. And we'll see examples in a second. This beta distribution, this posterior distribution for pi, represents all the likely values of pi given the information we have, all the information we have, the information that's provided by the sample, plus the information that I brought into the analysis through my prior. And so the equivalent to a confidence interval in the Bayesian world is called a credible set. And a credible set for pi is interpreted like you want to interpret it. It's the following. It says there's a 95% chance that pi is in this credible set. Notice the difference, right? In the frequentist case, the interpretation was, if I were to compute 100 confidence intervals, then 95 of those would cover the true value of theta, of pi. Here we say, I have one confidence interval and the chances that pi is in this confidence interval is 95%. It's quite different. And this is what, everybody wants to say, because this is the way we think. We don't think in terms, if I had 100 confidence intervals. So this is examples of the beta distribution. So for example, this is what a beta distribution. So this is, okay. In the x-axis, we have the range of possible values that the beta random variable can take on, and it goes between 0 and 1. And so the black curve here is the shape of the betas, depending on the values of A and B. So if A is equal to 1 and B is equal to 5, this is what the beta distribution looks like. And what does it mean? In this case, most of the values with higher probability are low values here. So by the time you get to like 0.5, which is here, values above 0.5 essentially have no probability, because the curve here is almost at 0. If you have a, and by the way, the blue line here, the solid line, is drawn at the mean. And the dotted line here is drawn at the mode, which is the most likely value. If you have a beta with parameters 1 and 2, so A is 1 and B is 2, this is what you get. This is what represents the likelihood of different values of the parameters. So here you have that the more likely values are also the smaller values, and the likelihood of observing a value goes down as pi increases. If we look at this one here, this is a beta 2020. So A is equal to 20, B is equal to 20. Look at this thing. It looks like a normal distribution. The mean is at 0.5. And what this is saying is you're most likely to observe values of pi in this range here. Anything above, let's say, 0.6 is unlikely. Everything below, let's say, 0.3 is also unlikely. This is an option that is used often, the beta 1-1. This is what we would call a non-informative choice. Why? Because this is what the distribution looks like. It's a straight line. And what is it telling me? It's telling me that so the height of this distribution is the same for all possible values of pi. So I am not choosing any value a priori as more likely than the other. Every value is equally likely. So essentially that means I don't have any information about theta before we collect data. And so this is a very nice model because you can play with the values of these parameters so that these distributions reflect your knowledge. So if I am pretty certain that pi is above 0.5, then I could use this model in the bottom. Because that gives high probability to values of pi above 0.5 and very low probability to values of pi below 0.5. If I am pretty certain that pi is below 0.5, I could use this top model over here. If I don't have a clue, I could use this model over here. If I think that pi is somewhere in the middle, but I am not very certain, I could use this model over here, because here every value of pi, let's say between 0.2 and 0.8 is likely, and the only values that are unlikely are very, very high values or very, very low values, and so on and so forth. So this one, it's very flexible model that allows you to represent your knowledge by depending on the values you pick for the parameters. So here is an example of the calculations that the base might do, the base person might do. So you might start, this is values of pi, and you might start with a prior, let's say that looks like this yellow distribution over here. So this might be your prior. And so what this is saying is, I think that pi is about what, 0.45 or something along those lines, because this is where the mean of that distribution is and the most likely value is. And I'm pretty certain that I'm right, because I am only, I think that the chances that pi is below, let's say 0.3 or above, let's say 0.55, those are very, very low. In fact, my prior essentially gives no weight to values below 0.3 or above 0.55. Now I collect data, and from the data, so this is subjective, completely subjective. I come up with this distribution on my own, the yellow distribution. The blue distribution here might represent, for example, the likelihood. And this blue distribution, I calculate using the sample data. So a priori, I thought that that pi was somewhere about 0.45, right? But the data is telling me that pi is about 0.6 or so, a little bit higher than 0.6. That's what the data tell me. And so once I combine the data information with the prior information, I get the posterior, which in this example would be represented by this green distribution in the middle. The posterior is always a compromise between the prior information and the data information. And how much each source of information contributes to the posterior depends on the sample size. The larger the sample, the heavier the influence of the data information will be than the prior information. In fact, if I have a very, very, very large sample, the data simply swamps the prior information. So the prior information is important and is influential when I have a very small sample. When I have a large sample, the prior information doesn't contribute much. All right. So here's some contrasting the two approaches in words. And this I took out of a paper by Colin Aitken that I thought was pretty good. So the binomial distribution is the probability model that the frequentist statistician uses to represent the distribution of the data, right? And so this gives us, what does it give us, the binomial distribution? This provides the probability of observing certain value of positive cases, Y, in the sample, given knowledge about the proportion of positives in the population pi. The Bayesians work with this beta model, this beta posterior distribution that results from combining the binomial with the beta prior. And what this beta model tells us is what are the likely values for pi given the number of positive values Y we observed in the sample. And so this is much more reasonable. This is the real question we have. I have the sample and I have some prior information. What do those two things tell me about the likely values for this population proportion pi that I cannot observe? So, all right, so this is all fine and dandy. The question is, how do we use all this stuff to do sample size calculation? And it turns out that it's not so easy. So one of the nice features of the frequentist approach is that, at least in the binomial case, when you have a large population and you can assume you're sampling with replacement and so on, you get a simple expression to estimate the sample size. Remember, we said you can solve for n, and for example, using this criterion that says, I want to have a margin of error no larger than, let's say, 3%. And so what is the n that will meet that criterion? And it turns out that in the simpler case, you get a very simple expression and you can calculate n in your calculator. You know, you can get the value of n in your calculator. It turns out that even in the simple case, the calculations are much less obvious if you're a Bayesian, and you certainly cannot do it on your calculator. So in this very simple case where I have a beta prior, a binomial likelihood, and that results in a beta posterior. Remember, I told you the posterior for pi is beta with parameters a plus y and b plus n minus y. The a and the b come from the prior. The y and the n come from the data. This distribution has a mathematical expression. There's, this is a function, a mathematical function. And the mathematical function looks like this. You get pi to the a plus y minus 1. You get 1 minus pi to the b plus n minus y minus 1. This is in the numerator. And then in the denominator, you get this thing called a beta function. And this is a function that has factorials, and it's kind of an icky function. And the problem is that this silly function depends on n. And so if I want to solve this expression for n, good luck. It's kind of miserable, to be perfectly honest with you. You can ignore this first term here because it doesn't have any n's. This one doesn't have n's, but n appears up here in this exponent, and worst of all, it appears down here. And so solving for n is non-trivial here. And you have to do it numerically. So you have to let the computer do it for you. And there's no easy way to do these calculations. I mean, we statisticians can do them because we know how to code this thing, but you practitioner probably wouldn't be able to do them unless you have some special tools that you could use. On the plus side, if you are brave or if you have a statistician that works with you, the required sample size to meet some criterion is usually much smaller than what you end up with from a frequentist approach. So that is, there's a payoff if you can do it. So, so in terms of implementation, it's not so easy. And I thought about trying to do it for today, but then I thought it would take me the rest of the course today, and I didn't want to spend all this time. So there's packages out there that will allow you to do estimation from a Bayesian point of view. And most of them require knowledge of some specialized software like R, but others don't. And so in general now it's becoming easier to be a Bayesian, at least in terms of estimating population parameters. But sample size calculation has not been, this is also complicated. And I don't know of any package out there that will allow you to do sample size calculation from a Bayesian point of view. And so I've been thinking that maybe we should write such a package and make it easy to use. So with a nice user interface. And the other thing that I was thinking is that perhaps we should think about teaching a course on R for forensic practitioners. Since R is becoming, you probably have heard about this, R is this software, and it's becoming so prevalent that I wonder whether it might be time to teach forensic practitioners on the use of R. Anyway, that's all I wanted to say. And I wanted to leave as much time as possible. Oh my God, way too long. Much time as possible for Joe so that he can show you some practical things and how to implement some of the things we talked about earlier. And Joe, I think I'm going to give you the floor.
I just want to thank everybody for sticking around to the very end of this sampling course. Hopefully it's been worthwhile for you. As Anthony said in the intro, my name is Joe Zemmels, and I'm a graduate research assistant at CSAFE. And I have been with CSAFE, I think now for 3 years as a graduate student, working on the cartridge case project. But another one of my, apologies by the way if you hear sirens, one of my many tasks that I work on is on developing materials for the various courses that CSAFE offers. And so I created this Excel lab, or Practicum, as we've been calling it, with the intention of sort of giving you all experience with using Excel, and in particular using Excel to kind of engage with the concepts that was covered, or some of the concepts that were covered in the course that you've been taking so far. So earlier today, you should have received an email containing a bunch of files, and these files should include a sampling course Excel lab PDF, as well as solutions to this PDF. And then additionally, you should have received a Excel file, 3 Excel files actually, one with called glass.xlsx, and then also solutions associated with that. And then finally, a calculator, as the file is called, that we'll talk about later on in this practicum. But anyways, the plan for today is I will be sort of walking through this practicum with you all, and I encourage you to engage with the practicum. Try to work through it as I am as well. Or if that doesn't work for you, if you'd rather just sort of sit and listen, feel free to do that, and then you can always come back to the recorded version of this presentation and try to work through the lab yourself using that. So let's go ahead and just dive in. So my plan is that I'm just going to kind of hop back and forth between this this write-up of the practicum and then Excel to show you kind of how you can solve the exercises in Excel. But this practicum is broken up into two pieces. So this first piece deals with sampling approaches, and in particular, we'll consider how various sampling schemes affect estimates for the population mean. So we'll dig into some of the different sampling schemes that Dr. Carriquiry talked about earlier in the course. And in the second part, we will talk about how we can calculate or estimate sample sizes using a special calculator that is available for free online. And I guess we'll kind of play it by ear. We may not have enough time to get through the entire thing, but that's all right, because there is actually a pre-recorded version of the solutions that I created that you can have access to if we don't get through everything. So anyways, let's go ahead and dig in. So this first exercise, as I said earlier, looks at various sampling schemes and how they affect estimates of the population mean. So we're going to take a look at this glass.xlsx file. So I'll go ahead and show you what this looks like now. So here's the file. You can see that this Excel file has three different tabs. The first one is just called glass, and then we also have SRS and stratified, which we'll get to later on in the exercise. But this main glass tab contains 4 columns. And these columns represent, the first column represents a manufacturer from which we obtained various panes of float glass. And so there were 2 different manufacturers in this study. And so we just denote those as manufacturer A and manufacturer B. And as I said, from each manufacturer, we obtained some number of panes. And those panes are uniquely identified by some alphabetic code. So pane AA, for example, is distinct from pane AAA. And so you can use that column to identify those panes. And then from each pane, we obtain 24 fragments. And so that's why the sort of groups of 24 observations in this data set. And then from each of those fragments, we measured the elemental concentration of the isotope manganese 55. And so that's what's being shown in the 4th column. So that is sort of the breakdown of this Excel file. I'll go ahead and jump back to the write-up here. I should say, so we are going to be making a simplifying assumption in this exercise, in that we are going to behave as if this entire Excel data set is our whole population of interest, meaning our population size is 1,147, because that's the number of observations that we have. And the reason why we're going to make this simplifying assumption is so that we can know ahead of time what the population mean is, and then for the various sampling strategies that we'll employ, we can then compare what the sample averages are to the true population average, being the average from the entire data set. So that's the plan for this exercise. And the rest of this just kind of details everything that I already described. So let's go ahead and look at the first exercise. And I should say, as I'm going through these, feel free to type in the chat if you do have any clarifying questions, whether you're following along or not. But first question here asks, what is the population mean? And then it gives us some ways that we can do this quickly in Excel. So I'm going to assume that some of you watching, maybe most of you, don't have a ton of experience with Excel. So I was hoping to sort of show you some tricks of how to perform calculations quickly in Excel. And so we will spend some time doing that. And the first trick that I want to show you all is how to use Excel formulas. So Excel formulas is a way that you can perform calculations in Excel, essentially. And the way you start an Excel formula is you just choose a blank cell and you press the equal sign. Now, this signals to Excel that you're about to perform some sort of calculation. So for example, what we can do is maybe just type 2 plus 2, right? And if we click enter, you'll see that Excel evaluates that formula to obviously the correct answer being 4. but that's just sort of a basic intro to Excel formulas. What we actually want to do is we want to calculate the population average. And again, since we're assuming that we have the whole population available to us, essentially what we're going to be doing is calculating the average of all of the manganese 55 concentration values that you see in this fourth column here. The fast way to do that is using something called the average function. So I'm going to type, typically in capital letters is how you want to do it in Excel, the word average, and the you can see here that Excel recognizes this as a function, and so it gives you a little description of what this function does. So it returns the average or the arithmetic mean of its arguments. And so what we mean by arguments is basically just going to be a set of numbers whose average we want to calculate. So, you know, I could type, for example, the average of 2 and 4, which is obviously 3, right? But we obviously don't want to calculate that in this case. What we want to do is we want to calculate the average of all of the values in this fourth column right here. And the fastest way to tell Excel that we want to grab all of the values in this column is to hover your cursor over the column B header that you see here. And you should see it turn into an arrow pointing downwards. If you click, you can see that Excel very quickly highlights all of the values in that column. And if we close the parenthesis and then click enter, you can see that it evaluates that formula. So this 56.994-ish, if we want to round to 3 decimal places, is the population average, okay? So that answers the first exercise. So going back here now, we're going to take a look at our first sampling scheme, which is what we called in the notes a convenience sample, which is a non-random sampling scheme in which, as the name implies, essentially we essentially take whatever data we can get our hands on that's easy to obtain. So in this case, let's suppose that it was easy for us to obtain 24 fragments from pane AA, but maybe none of the manufacturers were willing to part with more than just this one pane, okay? And so all we have to work with are these 24 fragments. And then we ask the question, well, if this were our sample that we obtained based on convenience, what would be the estimate of the population average? And then how does it compare to the true population average that we just calculated? So going back to the Excel spreadsheet, again, we're going to be using this average function. So I'm going to go a little bit quicker now that I've kind of talked through formulas. So again, I've just typed out the equals average and then open a parenthesis. And what I want to do now is grab all of the observations associated with this pane AA. So I'm going to go ahead and click and drag my cursor down while holding down the click. And you can see that it highlights all of the observations from row 2 down to row 25. So it's the first 24 observations. And then if I close the parenthesis and click enter, you can see that Excel evaluates that formula. And in particular, what we end up getting is this is a sample average that's equal to 18.356 abouts. And what you should be noticing here is that this sample average is not a great estimate of the true population average, right? We know the true population average to be about 56, and we're not getting a very good estimate with this 18. So this should hopefully raise some red flags in your head of, you know, maybe something else is going on that we need to explore a little bit more. So with that, let's continue reading through the problem statement. So we answered that question 2 sufficiently. Going down to question 3. So this exercise says scroll down to rows 743 and 744 in the data set, which marks the end of the manufacturer A data and the beginning of the manufacturer B data. So let's go ahead and do that. So let's scroll down here. Unfortunately, there's not, at least that I know of, a very quick way to scroll down to a particular line in Excel spreadsheet. If someone is more of an expert in Excel than I am in the chat, I'd be happy to hear. But anyways, here's line 743. And as you can see, it's sort of the end of the manufacturer A data. And then we start the manufacturer B data. Now, keeping this in mind, focus now on the values that are in that fourth column. What you should be noticing is that all of the manufacturer A panes of glass seem to have an elemental concentration that's like around 17, 18, 19. Right? And as soon as we start looking at the manufacturer B data, that elemental concentration jumps up to 127, 128, 129 parts per million, kind of in that range. And so this should again sort of raise some flags. It seems to be the case, and indeed, if you were to continue scrolling through and looking at these elemental concentration, it seems to be the case that the panes of glass from manufacturer B have a lot higher elemental concentration of this particular isotope compared to the elemental concentrations from the manufacturer A data. And so if we take a look back at the exercise here, it asks us, why might this explain what you observed in question 2? So in question 2, just to recap, let's scroll back up here. We noticed that the average that we were getting when we just used the manufacturer A pane was very small compared to the true population mean. And this can be explained because we've now noted that the manufacturer A panes tend to have a relatively small concentration of manganese 55, whereas the manufacturer B panes tend to have a larger concentration. And so if you were to average together a bunch of small values with a bunch of large values, that average is going to kind of fall in the middle, right? And that seems to be what's happening with this population mean. And this also explains why, if we were to just use a sample from manufacturer A, we would not be kind of capturing all of the information that we would need, because we'd be missing out on all of the values from manufacturer B. So this is sort of meant to illustrate some of the dangers of using a convenience sample, because, and I guess I do want to reiterate this multiple times, in real life, we would not know the true population mean. Right? This is a simplifying assumption that we're making for the sake of this exercise, but we wouldn't actually know what this is. And so by that logic, we would not know that this was that this 18.356 is a bad estimate of the true population mean. And so again, this is sort of the danger of using a convenience sample. So let's go ahead and look back now at the exercises. Okay, so now that we've looked at the simple random, now that we've looked at the convenience sample, we're going to switch gears and take a look at our first random sampling procedure called simple random sampling, which is something that we talked about in the notes. And so now we're going to take a look at this SRS table. And so I am going to kind of go through all of the steps of simulating simple random sampling. But if you get lost anywhere in any of the steps I'm doing, I'm basically just following along with these steps that are provided in the write-up. So feel free to read through that if you do get lost at all, or feel free to ask questions as well. So let's go ahead and jump back here. So we are taking a look now at this SRS tab, which is the second tab in the Excel spreadsheet. And all I've done in this first column is I've copied over those manganese 55 concentrations. And then I've also created a blank column that we're about to fill in called random. And then to the right here, you can see that I've created sort of 5 different samples. And what we're showing here is basically we are taking a sample average of a particular size. You know, we're basically averaging a certain number of rows, and then for the sample 1, and then sample 2, we're sampling the next. It's 50 rows in total, I should say. Each of these samples consists of samples of size 50 that we're using to calculate the average. And then sample 3 is the next 50 rows, and so on and so forth. And the intention of showing you 5 different sample averages is to sort of illustrate this idea of sampling error that that Dr. Carriquiry talked about in the slides, right? Where even if we get a great sample from our population, if we were to repeat that sampling procedure multiple times, we would still expect variability in the sample mean. And so that's what this is intended to illustrate, is that variability. So we haven't gotten to the simple random sampling part yet. And so the way we're going to do this simple random sampling is we are going to populate this random column with a sequence of randomly generated numbers. And in Excel, the fastest way, I think, to do it is to use something called the rand function. So you can type exactly what I've typed in the cell here, equals rand, and then we don't have to pass any arguments to this function. And if I click enter, you can see that Excel randomly generates a number between 0 and 1. Okay, and what I want to do is I want to repeat this formula all the way down to the bottom of the data set. Now, it is extremely tedious if I actually wanted to type equals rand all the way down, which I don't want to do. So here's a trick that you can use in Excel. If you want to copy a formula to the bottom of a data set, the way you can do that is if you hover your cursor over the little blue green square that's in the bottom right corner of the cell, you can see it turn into a black plus sign. And now if you double click, well, it's a black plus sign, it'll copy the contents of that formula. So now if I hover over, you can see that in the formula bar, all of these are the formula equals rand, okay? So there's a little trick. And now that we have generated some random numbers, what we want to do is we want to sort this data set of 2 columns based on the values of the randomly generated numbers. And by performing that sorting on the random column, that is equivalent to essentially just doing a random shuffling of the values in the manganese 55 column. Okay, and then from that, then we can draw a simple random sample. We can simulate what it would be like to draw a simple random sample by essentially just grabbing every 50 rows. Okay. So there is a little catch though, and this is something that's just a little bit of an Excel quirk, so to speak. And that is the fact that when you use a formula, what Excel actually saves under the hood is not the value, the numeric value that's shown in the cell right here. It's actually just the underlying formula equals rand. So if I were to click enter again, you can see it regenerates an entirely new random number for every cell. But what we want to do is we want to work with just a static set of numbers, ones that won't change. So the way you can make it so that Excel won't be saving the formula underneath, but the actual raw value that it shows in the cell, is you can copy the contents of that column. So what I've done is I've highlighted the entire column B again. And again, you do that by going up to the header and clicking once it's the downward facing arrow. And then you can click copy or Control-Command-C, depending on if you are a Windows or a Mac user. And then now that the values are copied, which you can see is the case because there's sort of this highlighting going on around the cells, we now want to paste the values from those cells. And if I click paste values and I look now at what the contents of the cell is, you can now see that Excel is actually saving the genuine decimal value that we want it to. And it does that for every single one of the cells in this random column. Okay, so that's just sort of a little quirk about Excel that's always important to remember when you're dealing with formulas. So the next step is, now that we've generated this set of random numbers in the random column, we are going to go and sort the values we're going to sort the rows of this data set based on the values in the random column. And there are different ways to do this. The way I'm going to show you is, because all of you should have on your various versions of Excel, you should have a data tab. So if you click that data tab, one of the options in the toolbar you should see is sort. So click sort, and maybe it's already filled in the sort by cell here, but we do in this window want to make sure that it says random. Sort by the cell values, and then it actually doesn't matter if it's smallest to largest because this was randomly generated. But go ahead and click OK once that's all set up. And now what you can see is we have a random, or the values in the random column are now sorted in order. And that means that the manganese 55 values are basically just have been randomly shuffled. They've been sort of permuted, is another way of saying that. And so you can see, for example, like here's an observation from manufacturer A, but then right afterwards there's one from manufacturer B, another one from manufacturer B, so on and so forth. And what you'll also notice is that these sample averages have now updated. And what you should notice is that the sample averages are now a heck of a lot closer to the true population mean, especially relative to that convenience sample average that we calculated previously. Now, what I'm going to do is, so in this cell E2, I have the text saying what the formula would be, just because I wanted to kind of show you what was happening underneath. But I'm going to actually make this into a genuine formula that Excel will evaluate just by putting the equal sign right before. And if I click enter, you can see it evaluates to that. So that's one thing to note, is that all of these sample averages, now that we've performed or simulated this simple random sampling, are now a lot closer to the true population mean than the convenience sample was. But one thing that's also useful to note is that the variability of these sample averages, that is sort of like the standard error of the sample averages, is relatively large. Like the true population mean, remember, is around 56, and these values range anywhere from like 46 to 62. Okay, and so we'll talk a little bit about why that might be the case and how we can employ a different sampling strategy to maybe make the standard error a little bit smaller so that the sample averages are a little less variable. So with that, that's kind of it for the simple random sampling procedure. And so if we now take a look back at the exercises here, so we've already answered this question 7. How do the sample averages compare to the population average? They're a lot better than the convenience sample, that's for sure. Now take a look at this question 8. There are 742 observations from manufacturer A and 405 observations from manufacturer B. Given this and your previous answers, why might it be appropriate to employ stratified sampling for this data set? Okay, so stratified sampling was a technique that we talked about in the notes. So I'm going to go ahead and show you where in the slides you can find this information. Starting on slide 52 of the notes, take a look at the slide immediately afterwards. This slide sort of discusses when stratified sampling is an appropriate random sampling strategy as opposed to simple random sampling. And in particular, this first bullet point says, when the population includes different types of items and some types are more abundant than others, a more efficient sampling strategy is to first stratify and then collect a random sample from each stratum, okay? So there are 2 things to note here. One is, we have almost twice as many observations from manufacturer A than we do from manufacturer B. So that sort of satisfies one of the criteria that were listed here. Some of the types are more abundant than others. And by types of data, what we mean is we've already noted that the manganese 55 concentration from the manufacturer A panes is very, very different from that of the manufacturer B panes, right? And so we can sort of think about this manufacturer variable as being a grouping variable that we should maybe separate the data into, okay? And so when we employ stratified sampling, we are going to have 2 strata, one for manufacturer A and one for manufacturer B. And we are going to use stratified sampling once we do that. And just as this slide illustrates or discusses, once we perform this stratification by manufacturer, all we have to do after that is just collect a random sample from each stratum. And that'll be how we perform stratified random sampling. So going back here, we've answered this exercise 8. And then the next step here is going to be go ahead and perform the stratified random sampling in the Excel tab. So let's go ahead and actually do that. I'm going to jump back here to the Excel spreadsheet. Now we're going to be focusing in on this 3rd tab, the stratified tab. There's a lot more information on this one, but really all I've done is I have copied over the manganese 55 concentrations separately for the manufacturer A panes. Those go into these 3 columns, and then the manufacturer B observations go into this, go into these 3 columns. And so that's all I've really done. And just as the slide said, all we're going to do now to perform this stratified random sampling is just repeat the simple random sampling procedure that we just discussed in the previous exercise, but we're going to do it twice, once for manufacturer A data and another for manufacturer B data. So I'm going to kind of quickly go back through this. Once you kind of get the hang of how to do this simple random sampling strategy, it does get a little bit easier. So again, that starts with using the RAND formula, hitting enter, copying the formula down, copying the contents of this column, and then pasting the values back in. And you can see now that it's the actual raw values rather than the underlying RAND formula that's being saved by Excel. So again, I did that very quickly, but that's just because, you know, once you get more practice with this, it'll go a lot faster. So now we're going to do the sorting procedure that we talked about before. So sort, we want to sort by the random column, by the cell values, and then smallest to largest is fine. And there we go. Now we have sort of a random shuffling. Oops, there we go. Now we have a random shuffling of the values in this manganese 55 column. And then we just do it again for the manufacturer B data. Copy, paste. I apologize if I'm going a little too fast for some of you, but hopefully I will sort of slow down on some of the other things coming up here in case you do need to get caught up. But there we go. So I have just done that in a lot faster than I did the first time. So now we sort of have this random shuffling of the values from manufacturer A and manufacturer B. So I'm going to go ahead and return now to the exercises to see what it prompts us to do. Okay, So suppose that our desired stratified sample size will be just the square root of the population size per stratum. I think in practice, what we would actually do is try to come up with a little bit more of like a principled way of calculating the stratified sample size, maybe using some of the sample size calculation formulas that we'll discuss in the second part of this practicum. But for now, let's just keep it simple and just say, let's take the square root of the population size. And so this exercise prompts us to now calculate the two stratified sample sizes. So let's keep in mind, we're going to take the square root of the population sizes, and we have a total of 742 observations from manufacturer A and 405 observations from manufacturer B. So we just have to take the square root of these values to find the stratified sample sizes, and then round up to the nearest whole number if needed. So going back now to the Excel spreadsheet, again, Excel is just a kind of a nice calculator. Obviously, you could do this with your own calculator if you wanted to, but Excel has some built-in functionality that allows us to calculate square roots. In particular, it has this SQRT function, square root, that all we have to do now is put in, and I'm already forgetting, 742, is that what it was? Yes, 742 is going to be the sample size for the manufacturer A data. This is our first stratum. And so rounding this up, we're just going to say that we're going to take 25 observations from manufacturer A. Okay. You don't have to type this. But, and then the next one is the square for the manufacturer B data. We're going to take the square root of that population size, which is 405. And then rounding up, we're going to take 25 observations from manufacturer B. Okay. All righty. So that's just how you can quickly calculate the sample sizes. Let's go ahead and take a look back just to make sure I haven't missed anything. Okay, perfect. So the sample sizes you calculated in question 9 have been pre-programmed into the formulas in column K. Explain in words what the unevaluated formulas in K2, K3, and K4 represent. So let's now take a look at where this exercise is telling us to look. So here's K2, K3, and K4. Again, these are function calls. Like we're asking Excel to use a function of some sort. We just have not turned this into a formula that Excel can actually evaluate. So let's take a look first at this cell K2. So it's clear that we're performing some sort of average. In particular, we're averaging values from column B of this spreadsheet, which is all of the manganese 55 observations for manufacturer A. And what we're doing is we're grabbing rows 2 through 29 of that data set. So another way of just saying this is we are collecting, or we are calculating the sample average based on a sample of size 28. Remember, that's what we calculated before. Because we did that random permutation that we did just a few minutes ago, this constitutes now a random sample from the manufacturer A data. So it's just a random sample from the manufacturer A data that we're taking an average of. So I'll turn that into a formula by putting the equal sign out front and click enter. And there's the evaluated value there. And then the same can be said about what's the contents of cell K3. This is now the average of the values in F, in particular, the first 21 observations, row 2 through row 22, from the manufacturer B data. And so just the sample average from the first 22, or from a random sample of size 22 from the manufacturer B data. So if we turn that again into a formula, put the equal sign out front and click enter, there we go, we have another sample average. And then K4 is a little interesting. So if you take a look back in the notes, in particular, I did write down which slide you can look at if you want to use this for future reference. If you take a look at slide 96 in the notes, I will jump down there. There we go. So this set of slides is all about estimation for the population mean from a stratified sample, which is precisely what we're doing, right? If you take a look at this slide 96, you can see that in order to calculate the overall population mean, all we have to do is take, this was explained sort of as like a weighted average of the sample means from each stratum, okay? And the weighting comes in to play by how large the stratum, each strata is, okay? And so if we now look back at the Excel spreadsheet, having recognized this formula, you can see that's exactly what we're doing here. We are taking 742, which is the number of manufacturer A observations we have, times the contents of cell K2, which is just this cell right here. This was the sample average from the manufacturer A panes. And then doing the same thing, but now with the manufacturer B data. There were 405 observations from manufacturer B, and we multiply that by the average that we calculate in cell K3. And then since it's an average, we then divide by the total population size. So making this into an evaluated formula and clicking enter, we now see that we have a sample there, a sample estimate of the population average. And there we go. So that is kind of in words what those three cells represent. So I'm going to go ahead and jump back now to the exercises. Oh, okay. And then I guess I kind of jumped the gun a little bit, because now question 11 tells us to put an equal sign in front to turn them into evaluated formulas. But then the next thing they ask us to do is, since we are calculating sample averages for the manufacturer A and B panes separately, we can go ahead and see how close we're actually getting by calculating the true manganese 55 concentrations for each manufacturer. So let's go ahead and do that. And then it asks us to kind of compare our sample averages to the true population averages. So let's go ahead and jump back to the Excel spreadsheet here. And I'll just do it over in this blank cell. So again, we're taking an average, but now we're just taking an average of just the manufacturer A data for this first one. So that's the contents of this column B. Okay, click enter, and we see it's about 18.07 is the true popular, 18.08 if you want to round, is the true population average for the manufacturer A data. And then, oops, not round. I said the word round. There we go. And then we also want to do the same thing, but then for the manufacturer B data. So another way, if you wanted to, here's just another trick. If you instead of wanting to drag your cursor, some people just like to use their keyboard. So you could always just type F:(F), and that would signal to Excel, grab all the contents of column F. Anyways, so there we go. So there is the true population average for the manufacturer B data. Now, the next part of this question was, let's take a look and compare how these sample estimates for manufacturer A and manufacturer B compare to the true population estimates. And hopefully it's clear to see that these sample estimates are really, really close to the true population estimate. So it turns out that within each manufacturer, the standard error that we would obtain from these sample estimates is quite small, right? Empirically, we can see that that is true, because all of these are sort of very close to the true values that we calculated in these two cells, okay? All right. Now, the final exercise then is compare the 5 estimated population averages to the true population average. How do these values compare to the convenience and simple random sample estimated values from before? So these cells here show the estimates of the population average based on the stratified sampling scheme. And again, I'm showing 5 of them just to kind of show you what the variability in the values are across multiple replications. Or repetitions, that is. And what we can see is that, again, the true population value is around like 56-ish. And you can see that these values are, again, extremely close to the true values. I guess all of them happen to be above 56, but I'm sure if we were to take another sample, it would be a different story. But the key takeaway from here is that they are all extremely close to 56, and the variability, that is the standard error of these population estimates, are extremely small. And so this is intended to illustrate that when stratified sampling is an appropriate, or when the conditions are met that justify the use of stratified sampling, it's best to use stratified sampling as opposed to simple random sampling. But that's only if you can identify, as we've done here, some systematic difference in the data based on some variable, where in this case, the systematic difference was that between the two manufacturers, the concentration was extremely different. So that's the key takeaway. Stratified sampling works well when you identify that it should work well, I guess is the main takeaway. Okay. And then the paragraph sort of at the end of this exercise here kind of just summarizes some of the things that I've already talked about. The big takeaway, I think that there's two big takeaways. One is, obviously, this was a very simplified version of what you would actually see in real life. And it was simplified mainly in the sense that we gave you the population up front. So we always knew what the true population average was, and we could compare our sample averages to that true population average. In practice, that wouldn't be the case. And so, for example, we wouldn't know that the convenience sample was such a terrible estimate of the true population mean because we wouldn't know what the true population mean was. And so, in general, a random sampling approach is almost always more appropriate. And if you identify any sort of grouping mechanism that exists in your data, such as manufacturer, then maybe try to employ something like stratified sampling. And then the last part is maybe for those of you who are familiar with Excel, or maybe even for those of you who weren't, this sort of random number generation process and the shuffling that we did, or the sorting process that we did, might seem a little tedious to you in Excel. And if it does seem tedious to you and you want to know if there's a better way, there certainly is, but you do have to learn what Dr. Carriquiry talked about earlier, which is this R programming language, which essentially makes this simple random sampling procedure trivial. But there's a little bit of, knowledge that you have to have before you can get to that stage. In particular, you have to know a little bit of how to use the R programming language. So anyways, I'm going to go ahead and pause there before we move on to the next exercise to see if there are any questions. I don't see any in the Q&A nor in the chat, but if you do have any, feel free to put some questions in the chat. For now, we're going to go ahead and move on with the last 30 minutes here of the course and talk about sample size calculation. The intention of this particular exercise is not to really dig deep into those various formulas that Dr. Carriquiry showed you in the slides. It's more so to make you aware of a useful tool that was developed at the European Network of Forensic Science Institute, specifically the drug working group there. They developed this Excel tool, this calculator for qualitative sampling of seized drugs. Its drugs was of interest for this particular working group, but this calculator can be used for much more than just drugs. But anyways, this is a very useful Excel tool that you can use in your own work to calculate sample sizes based on different goals of a study. So that's what we're going to be using today. So I guess before we dive into the actual contents of I'll go ahead and read through the exercise in just a sec here, but I do just want to say in the email that you received, you should have received this calculator for qualitative sampling of seized drugs already, but if you didn't, and maybe you just have the write-up of the lab, you can go ahead and this link takes you immediately to, or it'll initialize a download for you to download the calculator. So I'll go ahead and do that just to kind of show you what it looks like when you download the calculator fresh. And if we open it up, okay, so two things we have to do in order to actually make this calculator usable is we have to enable editing. And then we also have to enable content. So this is in particular enabling macros, which macros are just, you can think about that as like code that's running kind of behind the scenes that makes the calculator work the way it should. So we do have to enable that. And then you can see here that this Excel spreadsheet has various tabs down below, some of which we'll use. And then also this instructions is sort of the main page here that talks through a little bit about how you can use the calculator. But that will be kind of the content of this exercise is we will try to use the calculator to calculate sample sizes. So I'm going to go ahead and minimize this for now, and then we'll come back to it. That's the glass data. We're done with that for now. Okay, so reading now through the exercise. The mandatory minimum sentence for trafficking 1 gram of LSD in the US is 5 years in prison for one-time drug offenders. A common way to take LSD is by dissolving it into a solution, spraying the solution onto a sheet of blotting paper, cutting the paper into 1-dose squares or tabs, and ingesting one of these tabs. For this exercise, we're going to assume that 1 gram of LSD is equivalent to about 200 tabs. So reason being is I just wanted to simplify things and say, if you're caught with 1 gram of LSD, then we can apply this mandatory minimum sentence of 5 years. That was sort of my intention, making the simplifying assumption. But okay, continuing reading. Suppose that 300 suspected tabs of LSD were seized. It is to be established beyond a reasonable doubt whether at least 200 of the 300 tabs actually contain LSD. Due to time or budget constraints, it may be unreasonable to actually test all of the tabs. If we are willing to tolerate a little uncertainty, for example, a reasonable doubt, then we may be able to test considerably fewer tabs. Okay, and then we are, again, using this calculator that was developed by the European Network of Forensic Science Institute. And if you do want to learn more about the calculator outside of what we'll be talking about today, they actually have sort of a supplementary guide, so to speak, on how to use the calculator, and also a lot of other useful information about sampling at this UN guidelines for representative drug sampling. So I'd point you to that if you want to learn more. So this exercise is broken up into 2 pieces. The first piece looks at what Dr. Carriquiry explained in last week's course, which was the frequentist hypergeometric approach. And then the second piece, which if we have time, I'd love to get to, is actually looking at that Bayesian beta binomial approach that Dr. Carriquiry just talked about today. But we'll get to that if we have time. Okay, so the first one though is we're going to be using this, again, this frequentist hypergeometric approach, which as I understand it is by far the most popular method for calculating sample size. So in the calculator, we're going to be using a particular tab. So I'll show you that in just a sec. But essentially the way this calculator works is just like how any calculator works, I guess. And that is we're just going to be entering information into the calculator, and then it'll do some calculations behind the scenes and provide us with an estimated sample size. So taking a look now at the calculator, we're going to use this HypeG number tab for now. And there's a lot of information on this tab. Really, all you need to worry yourself with are these 5 cells that I've just highlighted. Cell B11 through B15, because this is where you enter in information. And so, the calculator even tells you kind of what you should be entering in. So enter the population size. Well, in our situation, we're dealing with 300 tabs of suspected LSD. So we type in 300, that's our population of interest. And then the number of positives, well, we want to show that at least 200 of these 300 tabs are positive for LSD. So we're going to enter in 200 as sort of like the lower bound on that. But it could be, 250 of them could be positive for LSD, or maybe all of them could be. But at least at a minimum, we want to show that at least 200 of them are positive. And then for now, we're going to assume that we don't expect any negatives in our sample. So we're going to keep this as 0. And then the confidence level is a little tricky to set. You will choose your confidence level largely depending on the context of the problem that you're dealing with and sort of maybe of the gravity of the problem. So if this is, going to, I guess the confidence level will depend largely on the context of how you're applying the calculator. But what we can think of is, again, we are to establish beyond a reasonable doubt that at least 200 of the 300 tabs are positive for LSD. And so if we think of a confidence level as being maybe 0.99, we might interpret the level of doubt that we then have to be 1 minus that value. So in this case, if it's a 99% confidence level, then our doubt level would be maybe 1%. That's not necessarily, that's sort of my interpretation of things, but that is not necessarily a well agreed upon interpretation of doubt. But for now, let's just suppose that we want a small level of doubt, meaning we want a high level of confidence. And so in particular, what I believe I say to do for this first exercise is just to keep this at 99% confidence. And then since we've entered in these 4 values into the cells here, behind the scenes, the spreadsheet was doing some calculations and it came up with this estimated sample size of 11. So what this means now is all we have to do is sample 11 of the 300 total tabs. And if all of them are positive for LSD, then we can say with 99% confidence that the number of tabs in the population that are positive for LSD exceed 200. That at least 200 of the tabs are positive for LSD, is another way of saying that. So that's sort of how we can use this calculator for the frequentist perspective. And so the calculated sample size in this case would be 11. And that'll be the same for all of us because we didn't do any sort of random sampling in this case. But now let's consider situations in which maybe like we change some of the facts a little bit and just see what the effect is on the estimated sample size. So for example, before we do any sort of testing, let's suppose that we anticipate that one of the sample tabs will be negative for LSD. And so that means that we're going to go ahead and change one of the values in the spreadsheet, and then we will assess how that affects the sample size change and then try to determine why that makes sense. So now going back to the calculator here, we're going to go ahead and enter in the number 1 into this particular cell because we expect one of the sampled tabs to be negative. And you can see now that the sample size has increased from 11 up to 17. And sort of the logic behind this, and Dr. Carriquiry did talk about this in the notes, so you can take a look back at the hypergeometric slides if you are interested in recapping this. But the idea here is if we obtain a sample and one of the tabs is negative for LSD, that means that there may be more tabs in the population that are also negative for LSD. So there's a little more uncertainty around the total number of tabs that are positive for LSD. And so we have to then sample more tabs so that we can retain the same level of confidence, in this case, 99%, okay? That's sort of the logic as to why we have to sample additional tabs. Okay, so that is the answer to that exercise. And then the next exercise says, so let's go ahead and change that value back to 0. And then consider that when we talk about what we mean by a reasonable doubt, maybe we're a little less restrictive than saying a 1% level of doubt. Let's say instead of saying a confidence level of 99, we switch that now to only a 95% confidence level. In which case the doubt level would then be 5%. And so then we ask the question, well, how does the sample size change and why does this make sense? So going back to the calculator now, change this back to 0. And instead of 0.99 in this step 4, we're going to go ahead and change this to 0.95. Click enter. And now you can see that the sample size has dropped from 11 down to 8. And the logic of this is, we are now not being as strict with our level of confidence. That is, we don't necessarily have to be as confident that at least 200 of the 300 tabs are positive for LSD, meaning we don't have to sample as many as we did when we were requiring a higher level of confidence. And so that's the logic behind why this sample size falls. And so the takeaway from this is the higher the confidence level, the more samples you'll have to take. All right. How are we doing? Okay, we got about 20 minutes left. I think that'll be enough time. So that's kind of the end of the frequentist hypergeometric approach. Like I said, this wasn't intended to be a super deep dive into that approach. It's more so just kind of getting you familiar with how to use the calculator. And in the last 20 minutes, I wanted to talk through this Bayesian beta binomial approach. Dr. Carriquiry said that it is difficult to find tools to perform Bayesian inference, which is definitely true. You pretty much have to use R if you want to do anything super complicated. But luckily, this calculator actually has a built-in functionality where you can use this beta binomial approach, the Bayesian approach, to calculate sample sizes. So that's what this exercise talks about. So hopefully this will be just a little bit of a recap of what we talked about earlier today in the notes. But we'll be using this particular tab in the calculator, this Bayesian, where the population size is greater than or equal to 50. It is the tab that we'll be using. So reading through here. So the first step in a Bayesian approach is to choose a prior probability distribution that the tabs are positive for LSD. So we're going to denote this with the notation P pos. So this is just, if we were to randomly select a tab from the population, what is the probability that that tab will be positive for LSD? And we have to choose a prior probability prior to doing any sort of testing of the tabs. We need to come up with some distribution that represents what our prior belief is that the tabs are positive for LSD. So the calculator uses the beta distribution that Dr. Carriquiry talked about in the notes today as the prior distribution. And there are two parameters of this beta distribution, A and B, that affect the shape of the probability density function. And you saw some of these examples in the slides on slide 149 in particular, if you want to take a look at that. But moving on here, so changing the shape of the probability density function can be interpreted as changing one's opinion of where the true probability that the tabs are positive is believed to lie. And since we're dealing with a probability that the tabs are positive, it's got to be somewhere between 0 and 1. But depending on our choice of prior, implicitly we'll be sort of representing whether or not we believe that this probability will lie maybe closer to 1, closer to 0, maybe somewhere in the middle. But we'll talk about that in just a moment. So, for example, let's suppose that we assumed that the probability here was equal to 1. So implicitly, or what this implies is that we are saying we are certain that all of the tabs are positive for LSD. That is, if we were to randomly select a tab from the population, if we assume that p positive is equal to 1, then that randomly selected tab we are saying will be positive for LSD. That is what our opinion is. Whereas if p positive is equal to 0, that means that we are certain that the tabs do not contain LSD. So the probability that a randomly selected tab will be positive for LSD is 0. So that is sort of the interpretation of these probabilities. The beta distribution parameters A and B are to be chosen by the examiner based on visual inspection of the tabs, other facts about the case, and the examiner's prior experience. This was something that Dr. Carriquiry talked about again in the notes. And one thing to note about this is that this is a very critical step in a Bayesian computation. And so it is oftentimes useful to sort of take into account, again, like your prior experience as an examiner. Maybe you've seen a lot of these LSD tab situations a lot in your past, and so that could inform your prior. You might know something else about the case that would push you one way or to the other into believing that the tabs are or are not positive for LSD, and you might just be able to look at the tabs and say, this looks like a tab, or this looks like blotting paper that would be positive for LSD if I were to test it. And so actually that's what this example looks at. So let's consider, for example, that LSD blotting paper commonly bear an artistic design. And then one such popular design is apparently the so-called man on bicycle design. So I'll just show you kind of what that looks like here. So apparently this is a popular depiction or art that goes on LSD blotting paper, is this man on bicycle. And so let's suppose that the 300 tabs that you see depict this man on bicycle design. Well, I guess I'm not an expert, I'm just a statistician, but I would say if something like that came in, I think you could be pretty certain that the tabs are positive for LSD if you were to test it. So anyways, the idea here is that you can incorporate that information into your calculations for the sample size. And the way you incorporate this information is by choosing a beta distribution that places more probability on values closer to 1. So we'll talk about that in just a sec here. But now let's actually get into the exercise part of it. So the following graphs show beta distributions for 4 different choices of A and B. Select amongst these 4 the most appropriate prior distribution in your opinion. Okay, and I say your opinion, and I point to the camera because it is your opinion. That is, there isn't one correct answer to the exercise, because the whole point of choosing a prior is that, again, it's based on your educated opinion. And really what you have to do is be able to justify your opinion as to why you chose that particular prior. But in the Bayesian paradigm, probabilities are subjective to the individual is sort of the idea. Anyways, the way that I kind of try to construct this example, though, there might be certain facts that I've given you that make some of the priors more appropriate over others. And so we're basically going to take a look here. And Dr. Carriquiry talked a little bit about this already in the slides, but I'm just going to kind of go back through. And for these 4 distributions, I'm going to kind of talk through what each of them represent. So all 4 of these are different versions of the beta function or the beta distribution. And so an important characteristic of all of these functions is that the area under the curve of each of these is always going to be 1. So, and for those of you familiar with calculus, what I mean is the definite integral from 0 to 1 is always going to be equal to 1 for each of these 4 curves, okay? And so just as Dr. Carriquiry talked about, let's take, for example, this, this plot in the bottom right, where we have sort of the distribution sort of peaks closer to 0 than it does down to 1. Hopefully it's clear to see that the area under the curve is, most of that area is sort of concentrated closer to 0 than it is to 1, definitely. And so the interpretation of this is that if we were to choose this distribution as our prior, we are saying that we believe that the probability that a randomly selected tab will be positive for LSD is small, close to 0, right? And that, again, is represented by the fact that most of the area under the curve is concentrated close to 0. And so by that logic, if this says that we believe that the probability that a randomly selected tab will be positive for LSD is small, this curve on the far left is kind of saying the opposite. It's sort of like the mirror of this curve that's on the bottom right. And so what this is basically saying is, and again, it's because the area is concentrated near 1, is we are saying that we believe that the probability that a randomly selected tab will be positive for LSD is high, is large, is close to 1, okay? And so so these two are sort of like competing opinions of each other in a sense. They have kind of opposite interpretations. What's interesting then is that if you take a look at the top right function, where in this case, A is equal to 0.5 and B is equal to 0.5, you can kind of see it's like a hybrid of these two distributions that are on the bottom here, where we have sort of part of the curve is sloping high up on the left, but then another part of it is sloping high up on the right. And so what this is saying is, you know, the area under the curve is concentrated on the extremes of the interval 0 to 1. So what this is implicitly saying is, we believe that either the probability that a randomly selected tab is positive for LSD is close to 1, or it's close to 0. And we're not really sure which one is which. You know, we don't necessarily have facts about the case or what have you, or to say whether one of those two hypotheses is more likely. Let's just make sure I didn't miss anything in that explanation there. Okay. So this is sort of like a more conservative opinion. That this beta distribution represents a more conservative opinion than these two do. And then just as Dr. Carriquiry talked about here, this distribution on the top left is just a horizontal line. And that's when A is equal to 1 and B is equal to 1. This is commonly called the uniform distribution. It is another term for this, and hopefully you can see why, because it's sort of like a uniform spreading of the area under the curve across 0 to 1. So this, again, just as Dr. Carriquiry said, this distribution represents an entirely like impartial opinion about the probability that a randomly selected tab will be positive for LSD. And so I guess I am not an expert, as I've stated earlier, but I would say it is rare in situations that an examiner would have absolutely no opinion about whether or not a tab is positive for LSD or not. If you know, if the tab landed on your desk, there's maybe a good chance that you should have maybe one opinion over another about whether or not the tab is, you know, positive for LSD. But again, if I'm saying anything out of turn, feel free to correct me on that. But anyways, in my opinion, I would say that in general, either B, C, or D is going to be an appropriate choice for a prior. Or something like this. You know, there are different versions of the prior, this beta distribution that Dr. Carriquiry pointed out. And in particular, again, I would say, based on the facts of the case, based on like at the moment, we're assuming that we have a blotting paper that has this man on bicycle design on it. I think we can be pretty certain that the tabs, if tested, would be positive for LSD. So I am going to go ahead and move forward with this exercise as if I chose this beta distribution where A is equal to 10 and B is equal to 1 as my prior. But you might have a differing opinion, and that's okay. You know, again, it's sort of all about justifying your choice in prior. Okay, so now moving on to the actual calculation here, and I know we have about 8 minutes, and I think we'll have just enough time to finish up here. So, because now that we've chosen a prior, which I know that was sort of a long drawn out process, but it is intended to be you have to be very careful with your choice of prior, making sure that your prior represents your actual opinion prior to observing any data. And so you do want to take the time to really think through the choice of prior, as we did. But once you do that, basically then the next step is pretty much the same as the frequentist hypergeometric approach, where we just end up entering information into the calculator. And that includes our choice of prior by choosing A and B. So let's go ahead and go back now to the calculator. And we're going to be using this tab, this Bayesian n greater than or equal to 50 tab. And we're just going to enter in kind of the same information that we did before. So the population size is 300. The proportion of positives in the population, again, we want to show that at least 200 of the 300 are positive, meaning at least 2/3 of them, right? So that's, 0.6 repeating, but we'll just say 0.666. The population is positive. Let's say we don't expect any negatives in the population. And then let's just suppose that our confidence level is going to be 0.9. So at the moment, we haven't actually entered any of the prior information in. Like we haven't said what our prior is. In order to change that, you have to change these two values here. So the prior that I chose, if you recall, had A equal to 10 and B equal to 1, okay? And once all that information is entered in, you'll see here that this is the estimated sample size. And so this, the estimated sample size in this case is only 2. So we only have to sample 2 of the 300 tabs to say with a 99% confidence, it says here, but it probably should say credibility because we're talking about in the Bayesian paradigm. But with 99% confidence / credibility that at least 2/3 of the tabs contain LSD. And so this hopefully illustrates to you just how important the choice of prior is in performing a Bayesian computation, because again, to reiterate, this prior that I chose represents the fact that I was already very confident that the tabs were positive for LSD, meaning I don't really have to test that many tabs to sort of verify that according to the data. And so this is one example, but now let's take a look here in the last couple minutes. Let's take a look back at the problem statement. So for me, the estimated sample size was 2, but I believe in the solutions, if you take a look at the solutions document, I do share what the other estimated sample sizes would be depending on what you chose as a prior. But now let's consider a situation in which instead of this man on bicycle design, which is sort of what I was using to choose the prior that I did, let's say we just had a blank sheet of blotting paper, just a white sheet of, or whatever color they come in, a blotting paper. What this means then is that we should probably, instead of being super confident that the tabs are positive for LSD, maybe we want to take a little bit more of a conservative approach and maybe allow for the possibility that none of the tabs are positive for LSD. And so we can use this information to choose a new prior distribution amongst the 4 previously presented, and then we'll see how that affects our sample size. So going back up here, I would say for these 4 that are being shown right here, if you chose this, this beta distribution on the bottom left, like I did, I would say kind of the next most conservative choice of a prior would be the one in the top right, this prior B, because you're still putting some belief in all the tabs being positive, but you're sort of sharing that with some of the tabs being negative. And then if you did choose prior B, for example, on your previous choice, then an even more conservative approach would be to choose prior D, which is saying, I don't think any of the tabs are positive for LSD. But anyways, let's suppose that with this updated information that we just have a blank sheet of blotting paper, that instead of the previous prior we chose, we're going to let A be 0.5 and B also be 0.5, and that'll be our new prior. So if we now go back to the calculator and update those values, so 0.5 and 0.5. So now you can see some stuff is updated. I haven't changed anything here, but now the sample size is actually quadrupled in size from what it was under my previous prior. And so this is representative of the fact that, now I'm a little less certain that the tabs are positive. So I need to sample more tabs in order to say with some level of confidence or credibility that at least 200 of the tabs are positive for LSD. So anyways, that's sort of that is a very brief introduction to the Bayesian paradigm of sample size calculations, but that is it for the exercises. And just in time, it looks like. So as I said, if you do have any questions, I'd be happy to answer them in the chat now. Otherwise, Anthony, I'm blanking on the email that they can send questions to if they have any.
They can send them to csafelearning@iastate.edu.
Thanks everybody for listening. Hopefully you learned something about Excel.
Joe, thank you so much for providing this practicum today. And Alicia, thank you again for your previous 2 sessions and today's session. Thank you all for joining us. We hope you have a great day.